This video is on integration using residues. In today's video, we are going to solve the problem using residue theorem. So in this video, we have to evaluate integral cot hz by z minus I into dz, where C is the circle, that is mod z is equal to 2. So here it is integral f of z into dz. Clearly our f of z value is given as cot hz by this is z minus I. Clear? So cot hz can be written as, so f of z is equal to cot hz can be written as cos hz by sin hz. So this is sin hz and already there is z minus I. Clear? And therefore our function is ready. So first of all we have to find the poles for this function. In order to find the poles, what we have to do? So we have to equate the denominator to 0. So that is z minus I into sin hz should be equated to 0. First of all, if I equate z minus I to 0 and next sin hz to 0, see what happens here. So z is equal to I, so which is a simple pole. So we got a simple pole. And next, when sign values become 0, so when z is equal to n pi, where n is equal to 0 plus or minus 1 plus or minus 2 and so on. See here, these are all the simple poles. So in general I am writing z is equal to, see here, z is equal to plus or minus n pi. So this is plus or minus n pi. So here among all these, so what is the circle given here? The circle is given as mod z is equal to 2. So here when mod z is equal to 2, z is equal to I and z is equal to 0. If I take 0 lies inside the circle. Clear? Lies inside the circle. Which circle? Mod z is equal to 2. Inside the circle mod z is equal to 2. Now we have to find the residues for these. So for finding the residues, as these are simple poles, see here residue of f of z at point z is equal to I is nothing but this is limit z tends to I. This is z minus I times of z minus I times of f of z. So what is our f of z here? So clearly f of z is cos hz by sin hz into z minus I. So this will be limit z tends to I. This is z minus I into this is cos hz by z minus I into sin hz. If I cancel this one and substitute I in place of z, so this will be cos hi by this value is sin hi. So cos hi minus sin hi is nothing but cot hi. So this is the residue value of f of z at point z is equal to I. So at point z is equal to I clearly. So this is a residue value. At the corresponding pole value z is equal to 0. And the next thing here is, so we have to find the pole, we have to find the residue at the pole value z is equal to 0. So in order to find the pole of z is equal to 0, clearly see, so this is the function value, and now residue at f of z at point z is equal to 0 is nothing but, see, first of all we have to write phi of 0 by xi dash of 0. The first function we have to take this as phi of z. So the first numerator is taken as phi of z and the next function is taken as psi of z. First we have to leave the numerator as it is and we have to derive the denominator and again substitute z is equal to 0 in this case. So first of all the numerator I am keeping as it is. This is cos hz. And the next one we have to make a derivative. So this is of the form u and this is v. That is z minus I am leaving, and for sin hz, so this value will be cos hz, and next this one for z this is 1, and for sin hz, see here I am leaving sin hz as it is. Clear? See here this is uv rule. So u I am leaving, v I am making a derivative, and again I am making derivative for u and leaving v here. So in this we have to keep z value as 0. So in this we have to keep z value as 0. So this will be cos 0 by this is 0 minus I into again cos 0 plus this value is sine 0. Cos 0 value is 1. So this is 1 by minus 1 and this value is plus 1. So this is minus 1 by I. It is the residue value of f of z at point z is equal to 0. At point z is equal to 0, so our residue value is nothing but minus 1 by I for z is equal to 0. So according to our residue theorem, now we have to use the residue theorem. So by residue theorem, according to our residue theorem, so we have integral f of z dz is nothing but 2 pi I into the sum of the residues at interior poles. See here. So what are the residues? So integral f of z dz. So integral f of z dz is nothing but this is 2 pi I into the residue at z is equal to I. So what is z is equal to I? This is cot hi. So this is cot hi, first one, and next one, this one is minus 1 by I. So this is minus 1 by I. So this is the answer. And what is our this one? F of z. So f of z value is nothing but cot z by z minus I. Therefore integral, this is cot z by z minus I into dz value is nothing but this value is 2 pi I into cot hi minus 1 by I. So this is the value which is needed. See, first of all we have to evaluate this function, that is integral f of z into dz, where z value is given by mod z is equal to 2. So f of z is cot z by z minus I and f of z is taken like this. And next one here, in order to find the poles we have to equate the denominator to 0. So after equating denominator to 0, we got z value as I and z value is plus or minus n pi, where n value runs from 0 plus or minus 1 plus or minus 2 and so on. So here what is our contour circle given? That is mod z is equal to 2. So inside the circle there are I and 0. So first of all we have to find the residues at the point z is equal to I. For z is equal to I, cot hi is the value, and next for z is equal to 0, so this is the case and this is the formula, that is phi of 0 by z dash of 0. Phi is nothing but the numerator and xi is nothing but the derivative of the denominator, and we have to keep z is equal to 0 and we got minus 1 by I, and therefore according to our residue theorem, so according to our residue theorem, integral f of z dz is nothing but 2 pi I into sum of the residues at the interior poles, and therefore 2 pi I into cot hi minus 1 by I. So this is how we have to solve. This is also most important question. Please practice and definitely pass it on to your friends. Please stay connected, and I'll be uploading many videos related to this residue theorem. Please practice those also. Thank you so much.